Part 1. The motion you cannot feel. There is something happening to you right now that your body is completely incapable of detecting, and if you could step outside yourself for just a moment and watch from a distance, it would look like the most dramatic, high-speed motion you have ever witnessed. You are spinning. Not slowly, not gently, not in any polite, barely noticeable way. If you are sitting anywhere close to the equator of this planet, your body is being carried sideways through space at roughly 1,674 kilometers per hour. That is faster than a military jet at cruise altitude. That is faster than the speed of sound in air, which clocks in at about 1,235 kilometers per hour. You are, at this very second, silently outrunning sound in a direction you cannot feel, cannot hear, and cannot detect by any sense you possess. And that is only the beginning. The ground beneath you is not just rotating on its own axis, it is also hurtling around the sun at about 30 kilometers per second. That is 108,000 kilometers per hour. The sun, which you might instinctively think of as a stable, fixed anchor at the center of our solar system, is actually moving through the Milky Way at roughly 230 kilometers per second. The entire galaxy is falling toward the Virgo cluster at approximately 600 kilometers per second. And somewhere underneath all of that, buried inside every atom making up your body, there is a layer of intrinsic quantum spin, a form of angular momentum built directly into the fabric of matter itself, that never winds down, never requires energy to maintain, and has been running without interruption since the universe was born. None of it produces the slightest sensation. The room you are in right now feels completely still. The walls do not vibrate. The air does not rush. There is no roar of wind, no sense of centrifugal force, no vertigo from being carried at 1,000 miles an hour through a night sky that looks like it is just sitting there. This feeling of stillness is not actually a failure of your senses. It is a very specific, very elegant physical property of the way rotating systems work. It is called an inertial reference frame, and what it means is this. When you are fully embedded in a system that is moving at a constant rate, rotating at a fixed angular velocity, accelerating so gently your nerves cannot register the change, your body has no information available to distinguish between being still and being on a very large conveyor belt. You are not wired to detect constant motion. You are wired to detect sudden changes in motion. The jolt of a car braking, the lurch of a plane hitting turbulence, those are detectable because they are abrupt changes in velocity. A smooth, continuous, unchanging rotation at a fixed rate produces nothing your nervous system can grab onto. So the planet carries you at 1,000 miles per hour and you feel nothing, and the atmosphere carries along right beside you so there is no wind against your face, and the oceans sit calmly in their basins because they are co-rotating with the same surface that is carrying you, and the whole thing has the texture of absolute stillness, while actually being one of the most dramatic kinetic events in the solar system. There is one small place where the rotation becomes visible, though, one crack in the illusion where the spin of the Earth writes its own name in something you can actually see. It is called the Coriolis effect, and you find it in the spiral arms of hurricanes and tropical cyclones. When a large air mass begins to move across the surface of a rotating planet, say, winds rushing inward toward a region of low pressure, those winds cannot simply travel in straight lines. The ground beneath them is rotating, and as the air travels across that rotating surface, the rotation deflects it. In the northern hemisphere, moving air deflects to the right. In the southern hemisphere, it deflects to the left. The result is that air does not pile straight into a low-pressure center. It spirals. Counterclockwise in the north, clockwise in the south. Every single hurricane you have ever seen on a satellite image, every tropical cyclone swirling over a warm ocean, is a direct visual proof that you are living inside a rotating reference frame. The spiral arms of those storms are the Earth's rotation signing its own signature in clouds. But even this is just the large-scale surface expression of something that goes far deeper. Because the rotation does not stop at the level of weather systems and planetary surfaces. It goes all the way down, through the crust of the Earth, through the molecular structure of rock and metal, through the scale of chemistry and biology, all the way down to the most fundamental layer of physical reality we currently understand. Inside every hydrogen atom in your body, and roughly 63% of the atoms in your body are hydrogen, there is a single electron orbiting a single proton. Both the electron and the proton carry something called quantum spin. This is not spin in the sense of a ball rotating on an axis. It is something stranger and more fundamental than that, and we will spend considerable time on exactly what it is later in this video. But in terms of its mathematical and experimental behavior, it acts like a form of angular momentum. It is an intrinsic property of the particle, built into its identity the way mass and charge are built into its identity. The electron does not spin up at some point and could theoretically stop. The spin is simply part of what the electron is. And this quantum spin produces a measurable, detectable signal that you can pick up with the right radio equipment anywhere in the universe. Most of the time, the electron and proton in a hydrogen atom have their spins pointing in opposite directions, because that is the lower energy configuration, the preferred, relaxed state. But occasionally, that electron will flip to align its spin with the proton's spin instead, a slightly higher energy arrangement, and then flip back down to the lower state. When it flips back down, it releases a photon. That photon has a very specific frequency, 1,420,405,751 Hz, 1.42 gigahertz precisely. Not roughly, not approximately, exactly. This frequency is so stable, so universal, and so reliable that radio astronomers have used it for decades as a standard beacon to map hydrogen gas across the Milky Way. Anywhere hydrogen exists, which is essentially everywhere in the observable cosmos, since hydrogen makes up roughly 75% of all ordinary matter in the universe, this signal is being broadcast. The universe is humming with a quiet radio tone produced by quantum spin. Every hydrogen atom, including the ones in your blood and your cells and the water you drank this morning, participates in this signal. The rotation is not happening to the universe. The rotation is built into the definition of the stuff the universe is made of. So let us be very honest about where we are at this early stage. Your body is being carried eastward at over 1,000 miles per hour on a rotating planet. That planet is orbiting a star at 108,000 kilometers per hour. That star is wheeling through the Milky Way at nearly 1,000,000 kilometers per hour. The galaxy itself is falling toward its neighboring cluster at over 2,000,000 kilometers per hour. And at the absolute bottom of all that motion, inside the atoms from which your body is constructed, there is a layer of rotation that never began and cannot end, that requires no energy to sustain, and that is not something matter does, but something matter is. The question is not why things spin. The question, when you actually sit with it and let it settle in, is whether anything, anywhere, ever stops. Drop a comment right now. Tell me where in the world you are watching from and what time it is there. I love seeing all the different places this reaches. And if you are new here, welcome. Hit subscribe so you do not miss what comes next. Part 2. The law that holds the whole thing together. There is a law in physics that sits at the center of everything we are going to explore in this video, and it is worth spending real time on, because once you understand it at a gut level, the behavior of everything from a spinning skater to a spiral galaxy starts to feel not just explained, but genuinely inevitable. The law is conservation of angular momentum. It states that in any physical system that is not acted upon by an external twisting force, the total angular momentum of that system remains constant. It does not decrease over time. It does not gradually leak away. It does not depend on whether the object is made of rock, gas, plasma, or subatomic particles. If there is no outside torque acting on the system, the angular momentum that was there yesterday is the same amount that is there today, and the same amount that will be there 1 trillion years from now. The most visceral illustration of this principle is probably the figure skater, and it has become something of a cliché in physics education for good reason. When a skater begins a spin with their arms extended outward, they rotate relatively slowly. The moment they pull their arms inward toward their body, they accelerate dramatically, sometimes reaching spinning speeds that look physically impossible. Nothing changed about the force being applied. No motor kicked in, no additional energy from outside the system entered the picture. All that happened was that the mass of their arms moved closer to the axis of rotation, and the laws of physics responded by increasing the rotation rate in exact proportion to how much that distance decreased. This is not a trick. It is not a coincidence or a clever engineering outcome. It is the direct, mechanical consequence of a conserved quantity being redistributed within a fixed boundary. The angular momentum of the skater was fixed. The moment they changed the distribution of their mass, the spin rate had no choice but to compensate. Now scale that up. A molecular cloud of gas and dust, the kind that forms solar systems, begins to collapse under the weight of its own gravity. The cloud has some slight net rotation, almost imperceptible, just the gentle leftover of turbulent random motions in the gas. As the cloud collapses inward, as its effective radius drops from something measured in light years down to something measured in astronomical units, that barely detectable initial rotation must be conserved. The spin rate increases in proportion to the square of the ratio of the radii involved. If the cloud starts with a radius of, say, 1 light-year and collapses to a disk a few hundred astronomical units across, the rotation rate amplifies by a factor so large that the original barely measurable spin becomes the dominant organizing force in the entire system. Material cannot fall straight in toward the center anymore. It has too much angular momentum for that. Instead, it spirals, settles into a flat rotating disk, and that disk is where planets eventually form. Every protoplanetary disk ever observed. Every ring system around a gas giant. Every flat galaxy seen edge on. Every accretion disk blazing around a neutron star or a black hole. Every spiral structure you have ever looked at in a photograph of the night sky. All of them are the same phenomenon. Angular momentum conservation, shaping the geometry of collapsing matter into flat, rotating structures. Because flat disks perpendicular to the rotation axis are the only shape that allows matter to continue orbiting while slowly spiraling inward. The disk is not an accident. The disk is the mathematical signature of angular momentum conservation written in matter. Gravity, left alone, would form spheres. The disk shape is what you get when angular momentum says no. But now let us go one layer deeper, because there is something even more profound underlying all of this. Why is angular momentum conserved in the first place? This is where one of the most beautiful results in all of theoretical physics enters the story. In 1915, the German mathematician Emmy Noether proved a theorem so sweeping in its implications that Einstein himself described it as a piece of penetrating mathematical thinking. Noether's theorem states, in its most general form, that every continuous symmetry of the laws of physics corresponds to a precisely conserved quantity. Read that again slowly. Every continuous symmetry, a precisely conserved quantity. If the laws of physics are the same today as they were yesterday, if the rules governing how matter behaves do not change over time, then energy is conserved. This is not a separate fact about energy that happens to be true. It is a logical consequence of the time symmetry of physics. If the laws of physics are the same here as they are 1 meter to the left, or 1 light-year away, if physics does not have a preferred location, then linear momentum is conserved. And if the laws of physics are the same regardless of which direction you are pointing, if physics does not have a preferred direction in space, no special axis that is more fundamental than any other, then angular momentum is conserved. These conservation laws are not rules that the universe chose to follow out of some cosmic good behavior. They are not empirical facts that physicists happened to measure and then wrote down. They are mathematical necessities that flow directly from the symmetry structure of the physical laws themselves. If the symmetry is there, the conservation law cannot be absent. They are the same thing, expressed in 2 different mathematical languages. The rotational symmetry of the laws of physics, the fact that an experiment pointing north gives the same results as the same experiment pointing east or up or at any other angle, appears to be exact, not approximate, not accurate to within measurement precision, and probably exact. Exact. Every experiment ever performed in particle accelerators, atomic physics laboratories, and astronomical observations of spinning pulsars has been consistent with exact rotational symmetry. The symmetry has never shown a crack. And because the symmetry is exact, the conservation law is exact. Angular momentum is neither created nor destroyed in any physical process anywhere in the observable universe. Not a single unit of it has been added or removed since the beginning of time. This means something remarkable when you think about it carefully. Every spin you can measure anywhere in the cosmos today, every orbiting planet, every rotating galaxy, every precessing quantum particle, carries angular momentum that has been in continuous, uninterrupted existence since before the objects carrying it were born. A galaxy that has been rotating for 12 billion years is carrying a record of the angular momentum that was present in the diffuse gas from which it formed. That gas was carrying a record of earlier turbulent conditions. Every spinning thing is a living fossil of motion that existed before the thing itself existed. Angular momentum is a cosmic memory system. It does not forget. It does not fade. It simply persists through every transformation matter undergoes, from gas cloud to star, to supernova, to neutron star, to whatever comes after. The universe keeps perfect books on this quantity, with an exactness that no other physical system in human experience comes close to matching, which sets up the first genuinely unnerving question this video is going to keep returning to. If angular momentum is perfectly conserved, and if every spinning thing in the universe today inherited its spin from something before it, and if that chain of inheritance stretches all the way back to the earliest moments of the universe, then there must have been angular momentum present at the very beginning. Somewhere, in the initial conditions of the cosmos, some angular momentum was present to seed everything we observe. The law can tell you that whatever was there at the start has been preserved, but it cannot tell you why anything was there to start with. The conservation law keeps the books. It was not present when the first deposit was made. Part 3. How a spinning cloud builds a world. Let us spend some real time with a collapsing cloud of gas, because this is where the abstract principle of angular momentum conservation becomes something you can almost hold in your hands. This is where physics becomes geology, and geology becomes living ground. About 4.6 billion years ago, in a quiet region of the Milky Way, there was a cloud of gas and dust a few light years across, mostly hydrogen, some helium. Trace amounts of heavier elements forged inside earlier generations of stars that had already lived and died before our solar system existed. The cloud was cold, perhaps only 10 degrees above absolute zero in some of its denser regions, and diffuse, spread across an enormous volume with a density that would register as a near-perfect vacuum by the standards of any laboratory on Earth. It was not perfectly still. Molecular clouds are turbulent. The gas within them has random, irregular velocities, tiny motions inherited from the dynamics of the galaxy itself, from the pressure waves of old supernova shockwaves propagating through the interstellar medium, from gravitational nudges delivered by neighboring clouds and passing stellar systems. The cloud as a whole had some slight net rotation, not much, almost nothing by the standards of anything you would call a rotating object in everyday life, but some. At some point, perhaps triggered by the pressure wave from a nearby stellar explosion, perhaps by the slow accumulation of the cloud's own self-gravity, the cloud began to collapse. Gravity pulled the densest regions inward. The collapse was not perfectly spherically symmetric, because the cloud was not perfectly spherically symmetric, and as the gas fell inward, the angular momentum it carried could not be shed. Here is the critical physical moment. As the gas fell toward the center, material approaching along the rotation axis, material that happened to be falling in from above or below the cloud's equatorial plane, had a relatively small component of angular momentum and could fall almost straight in toward the forming protostar at the center. But material falling in from the sides, material in the equatorial plane, had significant angular momentum. It was traveling sideways relative to the central concentration, and as it fell inward, that sideways motion amplified exactly as the ice skater's spin amplifies. The material could not simply pile onto the protostar. It had too much angular momentum for that. Instead, it was flung into a wide, circular orbit around the forming star, and as more material arrived in similar fashion, these orbiting particles and gas parcels collided, settled into a common plane, and formed a flat, rotating disk. The disk itself was not static. Gas and dust within it moved at different speeds depending on distance from the center, faster closer in, slower farther out, in the same way that Mercury orbits the Sun faster than Neptune does. Over time, small density variations in the disk caused clumps to form. Clumps attracted more material. Some of those clumps grew large enough for their gravity to dominate a local region, sweeping up surrounding material in a process called accretion. After tens of millions of years of these slow collisions and mergers, a process astronomers call planetary accretion, the clumps had grown into planets. Every planet in our solar system is essentially a compressed record of this process. The orbital planes of the planets all align within a few degrees of each other and of the Sun's equatorial plane. They all orbit in the same direction. These are not coincidences. They are direct legacies of the angular momentum in the original molecular cloud. The solar system inherited the rotation of its parent cloud and has been preserving it, in the form of orbiting planets and a spinning sun, for 4.6 billion years. The Earth's rotation today, its day, its axis, the direction the sun rises in your sky, is an echo of the net angular momentum in a cold cloud of interstellar gas that existed before the Earth, before the Sun, before anything recognizable as a solar system. The rotation was there first. The planet formed around it. Now consider what this means about the angular momentum problem in star formation, because this is a genuine open scientific puzzle that researchers are still actively working to resolve. If you take a molecular cloud core and measure its angular momentum, then measure the angular momentum of the star that eventually forms from it, the numbers do not match, not by a small margin. The star has dramatically less angular momentum than the cloud, sometimes by a factor of hundreds of thousands. If angular momentum were simply conserved in a naive, direct way during the collapse, the result would not be a star. The collapsing material would spin up so fast that centrifugal effects would halt the collapse entirely, leaving you with a large, rapidly rotating disk with nothing at its center. Something is carrying angular momentum away from the forming star. Several mechanisms operate simultaneously. Magnetic braking allows the magnetic field threading the collapsing cloud to act as a lever, transferring angular momentum from the inner collapsing region outward along field lines to the surrounding medium. Bipolar jets and outflows, spectacular streams of material launched perpendicular to the disk plane at hundreds of kilometers per second, which are routinely observed around young stellar objects, carry angular momentum physically away from the system. Disk viscosity and turbulence transport angular momentum outward through the disk, while material drifts inward. All of these mechanisms are real and observed. What is still not fully understood is the precise balance between them, and how efficiently each one operates under the specific conditions of a real collapsing cloud. The angular momentum budget of star formation is an active area of research, with observations from facilities like the Atacama Large Millimeter Array still revealing new structures in protostellar disks whose implications are still being worked out. The conservation law holds, the books balance. The mechanisms that do the accounting between them are still being mapped in detail. And now zoom out from a single solar system to the galaxy itself, because the same set of physics that builds a solar system from a collapsing cloud also builds a galaxy from collapsing intergalactic gas, and the resemblance is not metaphorical. It is literal. The Milky Way is a disk, a flat, rotating structure roughly 100,000 light-years in diameter, with the vast majority of its stars orbiting in a common plane in a common direction, with a central bulge and sweeping spiral arms extending outward through the disk. Every structural feature of the galaxy is the large-scale expression of angular momentum conservation operating on gas that fell together under gravity billions of years ago. The solar system orbits the center of the Milky Way at about 230 kilometers per second. At that speed, one complete orbit of the galaxy, a unit of time called a galactic year, takes somewhere between 225 and 250 million years. The Earth is about 20 galactic years old. Since the non-avian dinosaurs went extinct 66 million years ago, the solar system has not even completed a full third of one orbit. The galaxy turns with an unhurried patience that makes the timescales of human history feel like a single breath. But it turns. It turns because of angular momentum that was present in the matter that collapsed to form it, which was present before the Milky Way existed, inherited in turn from the large-scale dynamics of the early universe. Every rotation is someone else's inheritance. The chain runs in one direction, always backward, never breaking. And the beginning of the chain is where physics currently falls silent. Part 4. The impossible particle and the spin that defines matter. We have been talking about rotation at the scale of planets and galaxies. Now let us go in the other direction entirely, all the way down to the bedrock of physical reality, to the level where rotation stops being a motion at all and becomes something closer to the definition of matter itself. Every particle in the universe has spin. Every electron, every quark, every neutrino, every photon. Not as a property they acquired at some point in their history, not as a behavior they exhibit under certain conditions, but as a fixed, intrinsic attribute that is as permanently part of them as their mass or their electric charge. An electron cannot become a spin-zero particle any more than it can become a particle with a different mass. The spin is not something the electron does. It is part of what the electron is. This was not always understood. For a long time, physicists who noticed that atomic systems seemed to have angular momentum beyond what could be accounted for by orbital motion suspected there might be something missing in their models, but the mechanism was not clear. Then, in 1922, two German physicists named Otto Stern and Walther Gerlach performed an experiment that should have been entirely routine, but produced a result that, if you truly understand what they were expecting versus what they got, ought to feel like someone pulled the floor out from underneath classical physics. Their setup was straightforward. They took silver atoms, single atoms, vaporized from a heated sample, and passed them through a region where the magnetic field was strongly non-uniform. The logic was classical and intuitive. A silver atom has a magnetic moment, meaning it acts like a tiny bar magnet with a north and south pole. Pass a bar magnet through a non-uniform field, and it deflects, upward if the north pole faces one way, downward if it faces the other, sideways if it is oriented at an angle. A large collection of silver atoms, with their magnetic moments oriented in every possible direction, should produce a continuous, spread-out smear on the detector plate. Some deflected a lot upward, some a lot downward, with a continuous spread filling the space between. What Stern and Gerlach found was two spots, not a smear. Two sharp, discrete, separated dots on the detector plate. Exactly half the silver atoms deflected one way. Exactly the other half deflected the other way. Not gradually distributed, not filling a spectrum. Snapped into two specific outcomes with nothing in between. You could see the gap between the two spots with your eyes, and that gap was the physical proof, rendered visible on a piece of detector plate, that intermediate orientations did not exist. Whatever was responsible for the deflection was not allowing continuous values. It was quantized, it came in discrete steps, and the specific result of two beams, not one, not three, but exactly two, told physicists that whatever they were measuring had a quantum number of 1/2, producing exactly two possible measurement outcomes, up or down, with nothing between them. The problem was that no one understood exactly what property was producing the result. The Stern-Gerlach experiment was originally interpreted as measuring the orbital angular momentum of the outer electron in the silver atom. But the mathematics of orbital angular momentum predict an odd number of possible orientations, 1, 3, 5, depending on the quantum number, never exactly 2. 2 was the signature of something with a quantum number of precisely 1/2. Orbital angular momentum cannot produce half-integer values. 3 years later, in 1925, two young Dutch graduate students named Samuel Goudsmit and George Uhlenbeck proposed the explanation. The electron itself had intrinsic angular momentum, a property they called spin, separate from any orbital motion, with a value of exactly 1/2 in units of the reduced Planck constant. This gave exactly two possible measurement outcomes: spin up and spin down. It matched the Stern-Gerlach data. It explained the anomalous splitting of spectral lines that had been puzzling spectroscopists for years. The proposal fit. But there was an immediate catastrophic problem. If the electron has intrinsic angular momentum, if it is, in some sense, spinning, then the classical picture of a spinning object would suggest it is physically rotating. A charged sphere spinning on its axis would generate a magnetic moment, which is exactly what the electron has. So the picture seemed to be of a small charged ball rotating on its own axis. Goudsmit and Uhlenbeck worked out the numbers. For a classical charged sphere with the electron's measured charge, spinning with enough angular momentum to produce the observed magnetic moment, the surface of that sphere would have to be moving at a speed enormously larger than the speed of light. Not by a small factor, by several orders of magnitude. This was not a rounding error or a minor discrepancy. It was a complete and immediate physical impossibility. Special relativity does not allow any massive object to reach the speed of light. The classical spinning sphere model was ruled out by its own mathematics. Goudsmit and Uhlenbeck tried to withdraw the paper. They went to their supervisor, Paul Ehrenfest, and told him they had found a fatal problem. Ehrenfest had already submitted the paper for publication. He reportedly told them something to the effect that they were young enough to afford a foolish idea and that the paper would stand. It turned out the idea was not foolish. It was correct. The problem was not the spin. The problem was the model. Modern physics treats the electron as a point particle, an entity with no spatial extent, no radius, no surface, a mathematical point. A point does not spin in any geometrically meaningful sense. You cannot define a rotation axis for something that occupies no space. And yet the electron has angular momentum, precisely 1/2, always, measured identically, regardless of its velocity, its environment, or what experimental apparatus you use to probe it. The coherent theoretical framework that explained why a spinless, spatially extended classical model fails, while the point particle with intrinsic spin succeeds, came from Paul Dirac in 1928. Dirac was attempting to write a quantum mechanical equation for the electron that was fully consistent with special relativity, a project that had stumped the field because the existing Schrödinger equation worked beautifully at low velocities, but broke down at relativistic speeds. When Dirac wrote his equation, imposing the requirements of Lorentz invariance, the demand that physical laws look the same in all inertial reference frames, which is the mathematical core of special relativity, he found that the equation would not work with a simple two-component wave function. The mathematics of combining quantum mechanics with special relativity demanded a four-component wave function. Two of those components described the electron with spin up and spin down. The other two described a particle with the same mass as the electron but opposite charge, a particle that was theoretically predicted by the mathematics before it was ever observed in nature. That particle is the positron, the antiparticle of the electron, and it was experimentally discovered 4 years after Dirac wrote his equation, by Carl Anderson in 1932. Dirac had predicted the existence of antimatter as a mathematical byproduct of taking spin seriously at the relativistic level, without ever looking for it, without ever intending to predict it. It fell out of the structure of the theory the moment he combined quantum mechanics with special relativity. What the Dirac equation says, stated as plainly as possible, is this: spin is not optional. It is not a feature that could have been left out of the electron's description. It is not a quirk or an accident of nature. Spin 1/2 is the necessary consequence of requiring the electron's description to be consistent with both quantum mechanics and special relativity simultaneously. Any point particle governed by a relativistic quantum theory of the type that describes electrons must have spin. The spin is mandatory. The value 1/2 for the electron falls out of the mathematics whether you want it or not. Rotation, at this deepest level, is not a behavior that matter happens to exhibit. It is a structural requirement of what matter must be if the universe is both quantum mechanical and relativistic. The universe is both. So spin exists. The electron cannot be otherwise. Part 5. why you can touch things. Spin as the architect of reality. We just established that every fundamental particle has spin, and that for electrons and quarks and other particles of matter, this spin has the value 1/2. This is not a minor footnote. It is the reason the floor you are standing on does not collapse. It is the reason your hand does not pass through the table when you press it flat against the surface. It is the reason the atoms of carbon in your body do not simply fuse into a single, undifferentiated mass of compressed matter. It is, in a very literal sense, the reason you exist as a structured, solid object, rather than as a diffuse, formless plasma. The mechanism that converts spin 1/2 into structural reality is called the Pauli exclusion principle. It was formulated by the Austrian physicist Wolfgang Pauli in 1925, the same year Gaudsmit and Uhlenbeck proposed electron spin, and the connection between the two is not coincidental. The Pauli exclusion principle states that no two identical particles with half-integer spin, no two fermions, can occupy the same quantum state simultaneously. If two electrons are in the same atom, they cannot have the same set of quantum numbers. They can share the same orbital only if they have opposite spins, because opposite spins mean different quantum states. The moment both electrons would need to have the same spin to coexist in the same state, the Pauli exclusion principle forbids it, and one of them must move to a different energy level. This rule produces cascade effects that scale all the way from atomic structure to the solidity of matter to the survival of entire dead stars. Consider what it means for atoms first. If the Pauli exclusion principle did not exist, every electron in every atom would simply collapse into the lowest possible energy level, the ground state, the orbit closest to the nucleus. All atoms, regardless of how many electrons they contained, would have the same electronic configuration. Hydrogen, carbon, oxygen, iron, gold, all of them would look electrically identical from the outside, with all their electrons packed into the same lowest energy shell. Chemistry would cease to be a subject with more than one entry. But the Pauli exclusion principle means that electrons are forced to occupy a hierarchy of energy levels. The lowest level, the first shell, can hold at most 2 electrons, with opposite spins. Once it is full, any additional electrons must go to the second shell. That shell holds 8 electrons before it is full. Then the third shell, the fourth, and so on, each with a specific capacity, determined by the quantum mechanics of orbital angular momentum, combined with the constraint that no 2 electrons can share an identical state. The result is the electronic shell structure of atoms, and the shell structure of atoms is what produces the periodic table of the elements. The chemical properties of every element, its reactivity, its bonding behavior, the way it interacts with other atoms to form molecules, are determined by the number of electrons in its outermost shell, which is determined by how many electrons it has in total, minus the ones filling the inner shells, which is determined by the Pauli exclusion principle, which is determined by the half-integer spin of electrons. Chemistry exists because electrons have spin 1/2. The patterns of the periodic table, the reason water is a molecule and not just 2 hydrogen atoms rattling around near 1 oxygen atom, the reason carbon can form the 4 bonds that make organic chemistry and therefore life possible, the reason DNA has a double helix. All of this traces back in a direct mathematical line to the fact that electrons have spin 1/2 and cannot share quantum states. Now consider what the Pauli exclusion principle does at the macroscopic scale. Why does your hand not pass through the table? It is not primarily because of electromagnetic repulsion, though that plays a role. It is not because atoms are solid spheres that physically cannot overlap. In fact, an atom is mostly empty space, with the electron cloud occupying a volume that is roughly 10 to the 15 power larger than the nucleus at its center. The real reason is electron degeneracy pressure. When 2 atoms are pushed together close enough that their electron clouds begin to overlap, the electrons from both atoms would be forced into the same spatial region. But the Pauli exclusion principle means they cannot be in identical quantum states. As they are compressed together, each electron effectively resists being pushed into a quantum state already occupied by another identical electron. This resistance is not a force in the conventional electromagnetic sense. It is a purely quantum mechanical consequence of half-integer spin statistics. But it is real, and it is powerful, and it is what gives matter its solidity, its ability to resist compression, its capacity to hold the shape of a table or the structure of your hand. The proof that this is the correct explanation was provided mathematically by Freeman Dyson and Andrew Leonard in 1967. They showed rigorously that without the Pauli exclusion principle, ordinary matter would collapse, electrons would pile up into the same energy states, atoms would implode, and all the matter in the universe would compress into a volume unimaginably smaller than what we observe. The Pauli exclusion principle is, mathematically speaking, what holds matter up against its own self-gravitational tendency to collapse. This takes on an almost poetic significance in the context of stellar physics. When a star exhausts its nuclear fuel, gravity wins and the star collapses. But for stars similar in mass to the Sun, the collapse is halted by electron degeneracy pressure. The electrons in the collapsing stellar core cannot be forced into the same quantum states. They resist. The result is a white dwarf, an object roughly the size of the Earth, packed with a mass comparable to the Sun, supported entirely by the Pauli exclusion principle acting on its electron gas. A white dwarf is not held up by heat, not by pressure from ongoing nuclear reactions. It is held up by spin statistics, by the fact that electrons have spin 1/2 and cannot coexist in identical states. For stars massive enough that even electron degeneracy pressure cannot hold them up, the collapse continues until the electrons and protons are forced together into neutrons, and then it is neutron degeneracy pressure, the same exclusion principle, applied to neutrons instead of electrons, since neutrons are also spin 1/2 particles, that halts the collapse and produces a neutron star. An object roughly 20 kilometers in diameter, packing up to twice the mass of the Sun, supported by the same quantum mechanical consequence of spin that keeps your coffee cup solid on the table. If you want a single physical fact that captures the foundational importance of quantum spin, this might be it. The floor you stand on and the neutron star that will outlive the Sun by billions of years are both held in existence by the same property. The half-integer spin of fermions and the exclusion principle it produces are the structural skeleton of the material universe. Remove them and there is no matter. There is no shape. There is no you, no table, no earth. There is a featureless, perfectly undifferentiated plasma that has none of the properties we associate with the physical world. Keep them and you get atoms, chemistry, biology, and eventually minds curious enough to wonder why any of this is the way it is. Part 6. Galaxies that should not exist. Dark matter and the rotation problem. For a long time, the rotation of galaxies seemed like a solved problem. Galaxies form from collapsing gas clouds. The conservation of angular momentum shapes the collapse into a flat rotating disk. Stars orbit the galactic center in paths governed by the gravitational pull of all the visible mass concentrated toward the center of the galaxy. The inner stars move faster, the outer stars move slower, and if you plot their orbital velocities against their distance from the center, you get a curve that rises near the center and then declines steadily outward, exactly as the law of gravitation applied to the visible mass would predict. That was the expectation, reasonable, based on solid physics, confirmed by the behavior of the solar system, where Mercury zips around the Sun in 88 days, while Neptune takes 165 years. Exactly as expected, because the Sun's mass is concentrated at the center and the outer planets feel a weaker gravitational pull. Then the American astronomer Vera Rubin, working through the 1960s and 1970s with her collaborator Kent Ford, measured the rotation curves of spiral galaxies with a precision and scope that had not previously been achieved. She measured the orbital speeds of stars and gas at different distances from the center of galaxy after galaxy, starting with Andromeda, the large spiral galaxy about 2.5 million light-years away. She expected the familiar declining curve, the expected Keplerian drop-off. Stars far from the center moving slow. What she found, galaxy after galaxy after galaxy, was flat curves. Stars at the outer edges of galaxies were orbiting at essentially the same speed as stars much closer to the center. In some cases, the outer stars were even moving slightly faster. The expected decline never appeared. The rotation curve just kept going flat. This is deeply, profoundly wrong from the perspective of Newtonian gravity applied to visible matter. If the only gravitational mass is the mass you can see, the glowing stars and luminous gas, then stars at the outer edges of a galaxy are not just moving fast, they are moving so fast that they should be flung out into intergalactic space. The gravitational pull of the visible matter is not strong enough to hold them in their orbits at those speeds. By all rights, every large spiral galaxy should be slowly disintegrating at its edges, shedding stars into the space between galaxies. And yet no galaxy is doing this. They hold together, the outer stars stay put. The solution, which has become the cornerstone of modern cosmology, though the underlying particle responsible has never been directly detected, is that there is far more mass in galaxies than is visible. A vast halo of matter surrounds every galaxy, extending far beyond the visible disk, contributing gravitational pull that keeps the outer stars orbiting at the speeds Vera Rubin measured. This invisible material does not emit light, does not absorb light, does not interact with electromagnetic radiation in any way we can currently detect. We know it is there only because of its gravitational effects on the rotation of galaxies. We call it dark matter. Rubin compiled detailed velocity profiles for more than 75 spiral galaxies through the 1970s. Every single one showed flat rotation curves. The effect was not an anomaly. It was not a measurement error. It was a universal feature of galactic structure. The conclusion was inescapable. Every spiral galaxy is embedded in a vast, roughly spherical halo of invisible matter that outweighs the visible matter, and this invisible matter dominates the gravitational dynamics of the galaxy's outer regions. Dark matter has since been confirmed by multiple independent lines of evidence. Gravitational lensing, the way massive objects bend the path of light passing near them, a direct prediction of general relativity, shows that galaxy clusters contain far more mass than their visible components. The cosmic microwave background, the thermal afterglow of the early universe, has temperature fluctuations that are precisely consistent with models where dark matter makes up about 27% of the total energy content of the universe. Computer simulations of how the large-scale structure of the universe formed, the filaments and voids and galaxy clusters, reproduce the observed structure only when dark matter is included. And yet the particle itself remains undetected. Decades of experiments buried deep underground, designed to observe the rare occasions when a dark matter particle might interact weakly with ordinary matter and produce a tiny detectable signal, have run without a confirmed detection. Various candidate particles have been proposed: weakly interacting massive particles, axions, sterile neutrinos, primordial black holes. None has been definitively confirmed. There is an alternative hypothesis worth mentioning honestly, though it remains a minority position in cosmology. Modified Newtonian dynamics, proposed by physicist Mordechai Milgrom in 1983, suggests that Newton's law of gravity breaks down at the very low acceleration values typical of the outer regions of galaxies, and that a modified formula can reproduce the flat rotation curves without any dark matter at all. This approach works remarkably well for individual galaxies, and its predictive power for galaxy rotation curves is in some respects better than the standard dark matter model. But it works poorly for galaxy clusters, and it has not been successfully extended into a full relativistic theory that passes all the tests general relativity passes. The scientific community largely maintains that dark matter is a more consistent framework, though the debate has not fully settled. What both hypotheses share is this: galactic rotation is telling us something we do not fully understand about the mass distribution of the universe. The rotation curves are diagnostic. They are reading out the gravitational landscape of structures larger than the visible matter can account for. The spin of a galaxy is a fingerprint, and whatever left that fingerprint, dark matter, modified gravity, or something else entirely, is the dominant component of mass in the universe by a significant margin, and we do not know what it is. Vera Rubin died in December 2016 without receiving the Nobel Prize, which is not awarded posthumously. Many in the scientific community consider this a significant oversight. The Vera C. Rubin Observatory, built in Chile and beginning full science operations in 2025, is named in her honor and will survey the southern sky with unprecedented depth, contributing to ongoing dark matter searches. Her name is carried forward in the instrument, designed to push further into the mystery she opened. Every time you see a photograph of a spiral galaxy, you are looking at a rotation that should not be happening, at orbital speeds that the visible matter alone cannot explain, and at a structure that dark matter is holding together. Every spiral arm is a story about a quantity of mass that cannot be seen and has not yet been explained. Part 7. The Universe's Most Extreme Spinners. We have talked about the Earth spinning once every 24 hours, the Sun spinning once every 25 days at its equator, galaxies taking 225 to 250 million years to complete one rotation. These are the scales of rotation that are familiar enough to have names and feel approachable. But the universe contains rotating objects of a completely different character, objects where the conservation of angular momentum has produced speeds of rotation so extreme they strain the imagination and begin to test the physical limits of what matter can endure. The most dramatic spinning objects in the known universe are neutron stars. Specifically, a class of neutron stars called millisecond pulsars. When a massive star, significantly more massive than the Sun, runs out of nuclear fuel, gravity wins, and the star collapses in a fraction of a second in one of the most violent events in the universe, a core collapse supernova. The outer layers of the star are blasted away in an explosion that for a brief period can outshine an entire galaxy of 100 billion stars. The inner core, suddenly without the thermal pressure that was holding it up, implodes under gravity in milliseconds. Electrons and protons are forced together to form neutrons. The collapse halts when neutron degeneracy pressure, the Pauli exclusion principle applied to neutrons, resists further compression. What remains is a neutron star, an object roughly 20 kilometers in diameter, about the size of a city, containing between 1.4 and 2 times the mass of the Sun. The density is staggering. A teaspoon of neutron star material would weigh approximately 10 million tons on Earth. At the surface, the gravitational pull is about 200 billion times that of Earth's gravity. The escape velocity from a neutron star surface is roughly half the speed of light. And neutron stars spin. They spin fast, because of the same conservation of angular momentum that makes the ice skater accelerate when she pulls her arms in. The progenitor star was rotating before it collapsed. As the core imploded from an object perhaps the size of the Earth's orbit, down to something roughly 20 kilometers across, a reduction in radius by a factor of tens of thousands, the rotation rate amplified in exact accordance with conservation of angular momentum. Young neutron stars can spin many times per second. Some are observed as pulsars, objects whose magnetic poles, misaligned with their rotation axis, sweep radio and X-ray beams around the sky like a cosmic lighthouse, and whose pulses arrive at Earth with a regularity that rivals atomic clocks. But the truly extreme cases are millisecond pulsars, neutron stars in binary systems that have been spun up by accreting matter from a companion star. As material falls from the companion onto the neutron star, it carries angular momentum with it. The neutron star speeds up. Given enough time and enough accreted material, the neutron star can be spun up to extraordinary rotation rates. The fastest spinning pulsar, currently confirmed, designated PSR J1748-2446 AD, was discovered in 2004 in the globular cluster Terzan 5. It rotates 716 times per second, not 716 revolutions per minute per second. That is 42,981 revolutions per minute. To put this in some kind of physical perspective, at the equator of this neutron star, the surface is moving at roughly 24% of the speed of light. The neutron star completes one full rotation in 1.4 milliseconds. Theorists estimate that neutron stars could spin at rates up to about 2,000 rotations per second before the centrifugal force at the equator would overcome even the extraordinary gravitational binding of the object, and start flinging material off the surface. At 716 rotations per second, PSR J1748-2446 AD is operating at about 35% of this theoretical maximum. So far, no neutron star faster than 716 rotations per second has been definitively confirmed, though there are unconfirmed reports of bursting X-ray sources that may be spinning faster. Whether there is a physical mechanism preventing neutron stars from reaching their theoretical spin limit, or whether we simply have not yet found the fastest ones, remains an open question. Black holes also spin, and the constraints on their rotation are even more interesting. The spin of a black hole is characterized by a parameter typically written as which can range from 0, a perfectly non-rotating black hole, called a Schwarzschild black hole, to a maximum value where the event horizon of the black hole is rotating at the speed of light. A black hole at this maximum spin rate is called an extremal Kerr black hole, after Roy Kerr, who derived the general relativistic solution describing rotating black holes in 1963. Astrophysical black holes are observed to spin at substantial fractions of this maximum. The supermassive black hole at the center of the galaxy M87, famously the first black hole ever directly imaged, with the image released in 2019, is estimated from observations to be spinning at roughly 90% of the theoretical maximum. This spin has measurable effects on its surroundings, including a twisting of spacetime in the regions closest to the event horizon, a phenomenon called frame dragging. Matter falling into a spinning black hole does not fall straight in. It is swept along in the rotation of the spacetime itself, in a spiral that is forced into alignment with the spin axis of the black hole. Frame dragging is not a metaphor or an approximation. It is a direct prediction of general relativity. A spinning mass literally drags the fabric of spacetime around with it in the direction of its rotation. Near a rapidly spinning black hole, even light cannot travel in a straight line. It is pulled into a corkscrew path by the rotation of space itself. The universe's most extreme spinning objects are thus objects where the conservation of angular momentum has run forward through billions of years of stellar evolution, supernova collapse, and accretion, compressing and concentrating the original angular momentum of diffuse gas clouds into structures of staggering density, and producing rotations that test the physical limits of matter and spacetime alike. Part 8. How Galaxies Got Their Spin. The tidal torque story. We established earlier that angular momentum is conserved, that the spin of a galaxy is inherited from the angular momentum of the matter that collapsed to form it. But this raises a more specific question. How did individual protogalactic clouds acquire their angular momentum in the first place? The universe emerged from a hot, dense state after the Big Bang, and the distribution of matter in the early universe was remarkably uniform. What seeded the rotation of individual structures? The standard scientific answer is called tidal torque theory, and it describes one of the more elegant mechanisms in cosmological physics. In the very early universe, in the first tiny fractions of a second, quantum fluctuations in the density of energy produced slight variations in how much matter was in different regions. These variations were extraordinarily small, temperature differences in the cosmic microwave background of about 1 part in 100,000. But gravity is patient and relentless, and over time, slightly overdense regions attracted more matter from their surroundings. The overdense regions grew denser, the underdense regions grew more empty, and the large-scale structure of the universe, the cosmic web of filaments, sheets, and voids that we observe today, assembled from these tiny primordial seeds. Now, here is the key insight for galactic angular momentum. As a proto-galactic region of matter began to collapse under gravity, it was not collapsing in isolation. Neighboring overdense regions were collapsing at the same time, each one pulling gravitationally on the others. And because the mass distribution in these collapsing regions was irregular, not perfectly spherically symmetric, neighboring structures exerted gravitational tidal forces on each other. These tidal forces had a directional component perpendicular to the line connecting the two objects, producing torques, twisting forces, that transferred angular momentum between them. This process is called tidal torque theory, and it was first proposed by Fred Hoyle in 1949 and developed mathematically by Peebles, Doroshkevich, and White through the 1960s, 70s, and 80s. The essential prediction is that protogalactic structures acquire their angular momentum not from any primordial global rotation, but from the gravitational torques exerted by the irregular mass distribution of the early universe during the linear phase of structure growth, before the structures fully collapse and decouple from the surrounding matter. The crucial point about tidal torques is that angular momentum was not created in this process, it was exchanged. When one protogalactic region gains angular momentum from a tidal torque, the neighboring region that exerted the torque loses an equal amount of angular momentum in the opposite direction. The total angular momentum remains constant. Individual galaxies spin up, but every gain in angular momentum somewhere is balanced by a corresponding loss somewhere else. The universe's total angular momentum ledger is not changed by tidal torques. It is simply redistributed. Modern cosmological simulations confirm the broad predictions of tidal torque theory. The angular momenta of galaxy-scale dark matter halos are consistent in their statistical properties with what the theory predicts. But the details are more complicated. Galaxy spins show alignment with the large-scale cosmic web. Spiral galaxies tend to have their rotation axes parallel to the filaments they are embedded in, while more massive elliptical galaxies show a tendency for their angular momenta to point perpendicular to the filaments. These alignments are not fully explained by simple tidal torque theory and are active areas of simulation and observational research. What this tells us is that the angular momentum of every galaxy you can see in the night sky has a direct physical connection to the large-scale structure of the universe, to the filaments and voids of the cosmic web, which are themselves the grown-up versions of the quantum fluctuations that existed in the first tiny fraction of a second after the Big Bang. The spin of a galaxy is not random, it is not arbitrary. It is a preserved record, encoded in the angular momentum of billions of orbiting stars, of gravitational interactions that occurred over billions of years with the large-scale structure of the cosmos. The spin is a cosmic fossil. The galaxy is carrying the memory of the web in the direction it rotates. And the reason this memory has been preserved so perfectly, undistorted across the billions of years of galaxy formation and evolution, is the conservation of angular momentum. The same law that keeps a pulsar spinning at 716 revolutions per second also keeps a galaxy spinning for billions of years after its formation, without losing or gaining a unit of the angular momentum it started with. Part 9. The number that should stop you cold. Now we arrive at a fact that deserves to stop you completely. Not just pause you, but genuinely stop you, the way a truly strange idea sometimes does when you sit with it long enough to feel its actual weight. Take all the angular momentum in the universe, not abstractly, concretely. Add up the angular momentum of every galaxy in the observable universe, accounting for both the spin of each galaxy on its own axis and the orbital angular momentum of galaxies moving around each other within clusters. Add the angular momenta of all the stars, all the planets, all the neutron stars spinning at hundreds of revolutions per second, all the supermassive black holes rotating at near maximum rates. Add every spin at every scale, from the precessing quantum states of individual particles all the way up to the largest gravitationally bound structures ever measured. The answer, to within the measurement precision of everything we can currently observe, is zero. Not small, not negligible, not a tiny leftover from some approximate cancellation. Zero. In the precise sense that the positive angular momenta and the negative angular momenta cancel each other with extraordinary systematic accuracy. Galaxies spin in both directions in roughly equal numbers. Orbital motions in galaxy clusters are oriented in all directions, with no preference for one sense of rotation over another. The cosmic microwave background, the most precise all-sky map of the early universe, shows no large-scale asymmetry, no preferred rotation axis, nothing that would indicate the universe as a whole is spinning. The observable universe, as best we can measure it, contains approximately 2 trillion galaxies. Each one is spinning. And when you sum their angular momenta as vectors, accounting for direction, they cancel to zero within measurement error. Every individual piece spins. The whole is still. This is strange. Not superficially strange in the way that sounds strange but makes sense when you think about it. Genuinely, deeply strange. There is no obvious physical law that requires the universe to have zero net angular momentum. General relativity permits rotating universe solutions. We will get to one very shortly that is deeply uncomfortable. There is no known symmetry principle that obviously demands a net global angular momentum of zero. It is not an automatic consequence of the Big Bang itself, which expanded outward isotropically without imposing a preferred rotation on matter. One partial explanation comes from the same tidal torque theory we discussed for individual galaxies. If galaxies acquire their angular momenta through gravitational interactions with neighboring structures, and if those interactions always conserve the total angular momentum, transferring spin from one structure to another without creating any net new angular momentum, then the total angular momentum of the universe remains exactly whatever it was in the initial conditions. If the initial conditions had near-zero net angular momentum, the present universe will as well. But this just pushes the question back a step. Why did the initial conditions have near-zero net angular momentum? What physical process, what selection mechanism, what feature of the Big Bang or the inflationary epoch that followed it led to an initial state where the angular momentum was so precisely near zero? Some cosmologists argue that cosmic inflation, the period of extraordinary exponential expansion in the first tiny fraction of a second of the universe's existence, would have diluted any pre-existing global rotation to undetectable levels. If the universe started with some net angular momentum, inflation would have expanded the volume by a factor of at minimum 10 to the 78 power, spreading whatever rotation existed across a volume so vast that its density would be effectively zero in the observable universe. This would explain why we do not observe global rotation, not because the initial conditions were exactly zero, but because any initial rotation has been diluted beyond detection. The local angular momenta of individual galaxies would then be entirely due to tidal torques during structure formation, with no imprint of primordial rotation surviving. But this too is incomplete. We do not have a confirmed theory of the quantum birth of the universe that derives the initial angular momentum from more fundamental principles. We cannot calculate what the angular momentum of the universe should be from first principles and compare it to what we measure. The near zero is observed. It is consistent with several theoretical frameworks, but it is not yet derived from any underlying theory. There are even occasional observational hints that the cancellation might not be quite perfect. Astronomer Lior Shamir has published multiple studies analyzing large catalogs of galaxy images, arguing that galaxies rotating in one sense appear slightly more numerous than galaxies rotating in the other sense, roughly a 3% asymmetry in some datasets. If real, this would imply a slight global chirality in the universe's structure, which could indicate a weak residual global rotation. The mainstream cosmological community is skeptical. The asymmetries are small, the statistical methodologies are disputed, and systematic biases in automated image analysis could plausibly produce such effects. The question is scientifically open and will require larger, more carefully controlled surveys to resolve definitively. The possibility that the zero is only approximate, that there is a tiny residual global angular momentum hiding just below the current detection threshold, is not ruled out. And as we are about to see, even a tiny departure from perfect zero would have implications that go far beyond astrophysics, into the foundations of causality and the structure of time itself. Part 10. Gödel's Rotating Nightmare. On April 28, 1949, the mathematician Kurt Gödel presented a paper at a conference in Princeton celebrating Albert Einstein's 70th birthday. Gödel was already one of the most celebrated logicians in history. In 1931, at the age of 25, he had published the incompleteness theorems, two results that shattered the foundational program of mathematics by proving that any sufficiently powerful formal mathematical system must contain true statements that cannot be proved within that system. He had, in the span of a few pages, demonstrated that mathematics cannot be made complete and consistent simultaneously. He had found the limits of formal reasoning itself. Now, at Princeton, he had found something else entirely. An exact solution to Einstein's field equations of general relativity, describing a universe filled uniformly with matter, a cosmological model, like the ones used to describe the large-scale structure of the actual universe, but with one crucial difference. The matter in Gödel's solution was rotating, and in this rotating universe, something extraordinary followed from the mathematics. A traveler who followed the right path through space-time, accelerating in specific directions, curving appropriately, traveling what would feel like forward in time at every moment, could return to the exact same point in space-time from which they started. Not the same location in space after a long journey, the same event, the same moment. They would arrive back before they left. What Gödel had found were closed time-like curves, paths through space-time that loop back to their own past. In a rotating universe, the rotation of matter creates a gravito-magnetic-like effect on the causal structure of space-time. It tilts what are called light cones, the mathematical structures that define which events can causally influence which other events, in the direction of the rotation. As you move farther from the rotation axis, the light cones tilt more and more until, past a certain critical radius, they have tilted so far that a time-like path can close on itself. A path that always moves forward in local time can return to its own past. This is not a metaphor or a thought experiment about the strangeness of physics. It is a direct mathematical consequence of the Einstein field equations applied to a rotating matter distribution. Gödel did not add any new physics. He did not modify general relativity or introduce exotic matter. He applied the standard theory to a standard kind of cosmological model and found that rotation breaks causality. The implications are uncomfortable at a very deep level. Closed, time-like curves allow causal paradoxes of the type that have been a staple of science fiction, but that are profoundly troubling to physics. The grandfather paradox is the classic version. A traveler goes back in time and prevents their own grandparent from having children, which means the traveler was never born, which means the traveler never went back in time to prevent anything, which means the grandparent did have children. The logical loop cannot be resolved. Causality, the principle that causes precede effects, that the past is fixed and the future is open, is violated. Stephen Hawking proposed what he called the chronology protection conjecture, that the laws of physics conspire to prevent closed time-like curves from forming in any physically realizable scenario. His intuition was that quantum effects, specifically, the buildup of vacuum energy fluctuations in the vicinity of a closed time-like curve, would create catastrophic instabilities that destroy any structure approaching the conditions needed for time travel. The laws of physics, in this view, protect causality even if the classical equations of general relativity do not explicitly require it. The chronology protection conjecture has not been proven. It remains a conjecture, argued for on physical grounds but not derived from a full quantum theory of gravity. Whether it holds in all physically realizable situations is not currently known. To be clear, our universe does not appear to be the Gödel universe. We observe no closed, time-like curves. We observe no global rotation. The Planck satellite's mapping of the cosmic microwave background places the upper bound on any possible rotation rate of the universe at something like 10 to the negative 9 radians per Hubble time, meaning that if the universe is rotating at all, it has completed at most a billionth of a radian of rotation over the entire age of the universe. For all practical purposes, this is zero. We are not riding a Gödel universe. But Gödel's nightmare is important for this story, precisely because it tells us what is at stake in that zero. If the angular momentum of the universe were significantly non-zero, if there were a measurable global rotation, then the causal structure of space-time might be compromised. The arrow of time, the one-way flow from past to future that underlies thermodynamics and entropy and memory, and the entire structure of how events relate to each other in sequence, might not be a universal feature of the universe. It might vary with direction or position, tilting and bending with the rotation of matter, the way a magnetic field bends near a current. The precision of the zero we observe is, from this perspective, not merely an interesting cosmological datum. It may be a necessary condition for the universe to be the kind of place where time makes sense as a directed dimension, where the past is different from the future, where complex structures like biology and chemistry and consciousness can exist at all. A universe with significant global rotation might be too causally broken to produce observers. The observers who exist are necessarily in a universe where the global angular momentum is close enough to zero that causality is intact. This reasoning, that the observed properties of the universe are constrained by the requirement that observers be able to exist within it, is called the anthropic principle, and it is controversial in physics. Some find it deeply unsatisfying, a way of substituting selection effects for actual explanatory physics. Others argue it is a legitimate constraint that physics must account for. The debate is not resolved. What is not controversial is the physics itself. Rotation and causality are linked by general relativity in a very specific and uncomfortable way. The zero is doing important work, and we do not currently know whether the zero is an accidental feature of our particular universe's initial conditions, or whether it is in some sense demanded by the requirement that the universe be habitable. Part 11. Is space itself made of spin? We have been treating space as a stage, an empty container within which spinning things exist and move. Galaxies rotate inside space. Electrons spin inside atoms that exist inside space. Angular momentum is a property that objects carry around with them through a pre-existing spatial background. But what if that framing is fundamentally backwards? What if space does not contain spin, but is constructed from it? This is not fringe speculation. It is the serious, mathematically rigorous frontier of several of the most active research programs in theoretical physics today. And the idea, while deeply counterintuitive, has a kind of internal logic that becomes more compelling the more carefully you examine it. The framework that most explicitly develops this idea is called loop quantum gravity, and it was developed primarily by Carlo Rovelli and Lee Smolin, beginning in the late 1980s. Loop quantum gravity is one of the leading attempts to do something that has resisted physics for nearly a century: quantize general relativity. Apply the principles of quantum mechanics to the fabric of spacetime itself. Treat geometry, the shape and structure of space, the way quantum mechanics treats energy and matter, as something that comes in discrete, indivisible packets at the smallest scales, rather than as a smooth, continuous, infinitely divisible background. The result of this approach is a picture in which space, at the smallest scales, is not smooth and continuous. Space is a network, specifically, a structure called a spin network, a mathematical graph consisting of nodes connected by edges, where each edge carries a label, and that label is a value of quantum spin. Here is the part that should genuinely alter something in how you think about physical reality. Those spin labels on the edges of the network are not decorations. They are not bookkeeping identifiers for otherwise undescribed connections. The spin values on the edges are the geometric properties of the space the network represents. The area of a surface in loop quantum gravity is determined by the spins of the edges that pierce it. Specifically, if an edge with spin value j punctures a surface, it contributes an area proportional to the square root of j times j plus 1, multiplied by the Planck length squared. The Planck length is approximately 10 to the negative 35 meters, so unimaginably small that if you magnified a single atom to the size of the observable universe, the Planck length within that atom would still be smaller than the atom was originally. The volume of a region of space is determined by the spin values at the nodes contained within it. Both area and volume are quantized. They come in discrete smallest units, below which the concepts of area and volume simply cease to have meaning. This means that if you could somehow zoom into space with infinite resolution, if you could shrink yourself down past atoms, past nuclei, past quarks, past every scale at which physics has ever been tested, all the way down to the Planck scale, you would not find smooth, featureless, empty space. You would find something more like a discrete foam, a network of nodes and edges with quantum spin values, a granular structure below which there is no further structure to find. Space does not divide infinitely, it has a bottom. And the apparent smoothness of space at every scale we have ever actually probed from the millimeter scale of everyday experience to the megaparsec scale of cosmological surveys, is an emergent approximation. It is the smoothness that arises when you average over a vast number of these discrete, quantized, spin-bearing edges and nodes. The same way the smooth surface of water at the macroscopic scale is an average over the discrete molecular structure below. As Carlo Rovelli wrote about spin network states, a spin network state is not in space. It is space. It does not describe space. It is what space is. The implication is extraordinary. In this picture, when you ask why everything in the universe spins, you are not asking why things placed inside a fixed spatial stage happen to be rotating. You are asking about the property from which the spatial stage itself is constructed. Spin is not something that happens in space. Spin is what space is assembled from, at the level of discrete quantum geometry. A related approach, arrived at from a completely different direction, is called twistor theory, developed by the mathematical physicist Roger Penrose, starting in the 1960s. Penrose was motivated by a different puzzle. Why do the mathematical languages of quantum mechanics and space-time geometry feel so foreign to each other, as if they are describing fundamentally different things? Is there a more fundamental mathematical structure that would make both of them feel natural and unified? What Penrose found was that you could describe the fundamental objects of physics not in terms of points in space-time, but in terms of objects he called twistors, geometric objects that encode a combination of momentum, energy, and angular momentum as a single, unified quantity. In twistor space, the primary mathematical objects are directed spinning structures, and events in space-time, the points that feel so primary and fundamental in our direct experience, are actually derived quantities, constructed from the intersections of twistors. Space and time events are secondary in twistor theory. The spinning structures are primary. The geometry of space-time is a projection of a more fundamental rotational algebra. Twistor theory had a complicated history after its initial development. For decades, it was a beautiful mathematical framework that struggled to accommodate the full range of physical interactions. Then in 2003, Edward Witten showed that string theory amplitudes, the quantum mechanical probability calculations for particle interactions, could be reformulated in twistor space with remarkable elegance and efficiency. Modern calculations in particle physics, the computations that predict the outcomes of experiments at the Large Hadron Collider and other particle accelerators, are now routinely performed using twistor-inspired methods that are orders of magnitude more computationally efficient than the traditional approach. The mathematics of angular momentum, taken as a foundational object, is currently the most powerful language physicists have found for describing how particles interact. Both loop quantum gravity and twistor theory arrive at a similar conclusion from different starting points. Spin and angular momentum are not properties of objects existing within a pre-existing spatial framework. They are, in some deep mathematical sense, prior to that framework. The geometry we experience as the three-dimensional space around us is constructed from, or at least deeply intertwined with, quantum spin. These frameworks are incomplete. Neither has yet made a confirmed experimental prediction at scales where its specific quantum gravitational features would become directly observable. The Planck scale is 16 orders of magnitude smaller than the smallest scales current particle accelerators probe. We are not going to be testing spin network geometry in a laboratory in the near future. The territory is genuinely speculative, in the honest scientific sense of being mathematically serious and physically motivated, but not yet experimentally confirmed. But it is the direction in which serious physics is pointing when it asks what space actually is. And the answer that keeps emerging, from multiple independent approaches by researchers working at the most mathematically rigorous frontier of the discipline, is spin is more fundamental than space. Angular momentum is not something that lives inside the universe. It is something the universe is made of. Part 12. Emmy Noether and the Origin of All Conservation Laws. Before we reach the final synthesis, it is worth pausing to honor the person whose mathematical work provides the deepest foundation for everything we have discussed. Because the conservation of angular momentum, the principle that unifies every spinning thing in this video, from the electron in your hydrogen atom to the galaxy above your head, is not just an empirical observation that physicists measured and wrote down. It is the logical consequence of a theorem proved by a mathematician who overcame more obstacles than most people in her field had to face, and whose work was described by Einstein as the most significant creative mathematical genius thus far produced. Emmy Noether was born in 1882 in Erlangen, Germany, into a family of mathematicians. Women at the time were not officially permitted to enroll in German universities. She attended lectures by special permission, passed her doctoral examination in mathematics in 1907, and spent years working without pay, forbidden from formal academic positions because of her gender. When she eventually obtained a position at Göttingen, the most prestigious mathematics department in Germany, David Hilbert had to argue with colleagues who objected that students could not be allowed to study under a woman, reportedly responding that he did not understand why the gender of the candidate should affect the assessment of her mathematical work. In 1915, working at Göttingen, in the same department where Albert Einstein was developing general relativity, Noether proved the theorem that now bears her name. It states that every continuous symmetry of the laws of physics corresponds to a precisely conserved quantity. The word continuous here is doing important work. It means that the symmetry involves a smooth, continuously variable parameter, like the angle of rotation, which can take any value from 0 to 360 degrees without jumping, rather than a discrete symmetry like the reflection symmetry of a snowflake, which has specific discrete reflection axes. Continuous symmetries, in Noether's theorem, produce conservation laws. Discrete symmetries produce other important physical constraints, but not conservation laws of the type we are discussing. Time symmetry, the fact that the laws of physics work the same Tuesday as they did Monday, gives you conservation of energy. Energy conservation is not a separate law of nature that happens to be true. It is the mathematical consequence of the fact that physics does not change over time. You cannot have one without the other. Translational symmetry, the fact that the laws of physics work the same here as they do 1 kilometer to the left, gives you conservation of linear momentum. Move an experiment slightly, and the experiment gives the same results. That symmetry, in Noether's theorem, is conservation of momentum. Rotational symmetry, the fact that the laws of physics work the same regardless of which direction you point your experiment, gives you conservation of angular momentum. Physics has no preferred axis. Therefore, angular momentum cannot be created or destroyed. Einstein called Noether's theorem a piece of penetrating mathematical thinking. The physicist Lee Smolin has described it as one of the most important theorems in all of physics. It is not an overstatement to say that it provides the deepest foundation we currently have for understanding why the universe's physical quantities are what they are. But Noether's theorem, for all its power, has a boundary. It tells you how angular momentum evolves once it exists. It tells you that angular momentum present in the universe today must equal angular momentum present in the universe yesterday, and the day before that, and at the beginning. It does not tell you why any particular amount of angular momentum was present at the beginning. Conservation laws govern evolution. They are silent on origin. This is not a failure of Noether's theorem. It is simply outside the scope of what it addresses. The laws of physics describe how systems evolve from their initial conditions. The initial conditions themselves are the starting points for that evolution, the boundary values given to the equations. They are not outputs of the equations. They are inputs. The symmetry dictates what happens to the angular momentum once it is there. The first moment remains outside the frame. Part 13. The question physics cannot yet answer. Let us take an honest inventory of where we actually are. We know that every particle in the universe has spin. Every electron, every quark, every neutrino, every photon carries an intrinsic quantum angular momentum that is as fixed and fundamental as its mass or charge. This spin is not acquired at some point in the particle's history. It is demanded by the mathematics of combining quantum mechanics with special relativity. The Dirac equation does not accommodate an electron without spin. Spin 1/2 for the electron falls out of the structure of relativistic quantum theory, whether you want it to or not. We know that angular momentum is conserved with exact precision in every physical process. Not approximately, exactly. This follows from Noether's theorem and the exact rotational symmetry of the laws of physics. The fact that physics does not have a preferred direction. Every test of angular momentum conservation in particle physics, atomic physics, and astrophysics has confirmed this. Not a single confirmed exception exists anywhere in the experimental record of physics. We know that every gravitationally bound structure in the universe rotates. Planets orbit and spin on their axes. Stars rotate, young ones fast and old ones slow, but none of them still. Binary stars orbit each other. Galaxies spin as coherent disks. Galaxy clusters contain galaxies, orbiting their common center of mass. Accretion disks blaze around neutron stars and black holes. Every structure that formed by gravitational collapse from a precursor, with any angular momentum at all, has inherited, amplified, and preserved that angular momentum through the entire process of its formation and evolution. We know that the spin of every galaxy is traceable, in principle, through tidal torque theory and the conservation of angular momentum, all the way back to quantum fluctuations in the energy density of the universe during the inflationary epoch, a period in the first tiny fraction of a second of the universe's existence when the cosmos expanded by an extraordinary factor in an unimaginably short time, locking in the patterns of density variation that would eventually become the large-scale structure of the universe and the seeds of all galaxies within it. We know that the total angular momentum of the observable universe, as best we can measure, is 0. 2 trillion galaxies, each spinning, and their angular momenta cancel to 0 within measurement precision. Every individual piece spins, the whole does not. We know, from Gödel's work, that a universe with significant global rotation would be a qualitatively different kind of universe, one where the causal structure of space-time is compromised, where closed time-like curves exist in the geometry, where the distinction between past and future can become ambiguous. The near-zero angular momentum of our universe is, at minimum, consistent with the requirement that causality work cleanly enough for complex structures, chemistry, biology, consciousness, to exist at all. We know, from loop quantum gravity and twistor theory, that two of the most serious and mathematically rigorous approaches to the deepest open problems in theoretical physics suggest that spin is not a property of matter existing within a pre-existing space, but is in some sense the fundamental ingredient from which space itself is constructed at the Planck scale. The geometry of the universe may be an emergent average of a discrete network of quantum angular momentum relationships. Space may be assembled from spin, not the other way around. And here is what we do not know. We do not know why the universe began with the angular momentum it began with. Why not more? Why not less? Why not exactly 0 at every scale, leaving no rotation anywhere? Why not some large positive value that would have produced a rotating universe, with all the causal complications Gödel described? The conservation law tells us that whatever was there at the beginning has been preserved. It cannot tell us why anything was there to preserve. We do not have a confirmed theory of quantum cosmology that derives the initial angular momentum of the universe from more fundamental principles. The Hartle-Hawking no-boundary proposal, which suggests that the universe did not have a singular beginning in time but emerged from a quantum geometry without a boundary, is one attempt to address initial conditions, but whether it correctly predicts the angular momentum content of the universe is not known. It remains a speculative framework, one of several, none confirmed. We do not know whether the near-zero global angular momentum is exactly 0 or merely very close to 0. Our measurements cannot resolve the difference. The observational hints from some galaxy surveys of a tiny directional preference in galactic spins, if real, would imply it is merely close to 0. But those hints are contested and may well be measurement artifacts. The question is genuinely open. We do not know why the universe's rotational laws, which are so exact and so universal, took the specific initial conditions they took. The laws describe the evolution perfectly. The origin of the thing being evolved is outside the frame. There is something both deeply satisfying and deeply strange about where this leaves us. We have followed rotation from the floor you are standing on, to the quantum state of the electrons in your body, to the blast of a millisecond pulsar, to the spiral arms of galaxies 10 billion light-years away. We have traced it backward through billions of years of cosmic structure formation to quantum fluctuations in the primordial soup of the infant universe. We have found it encoded in the structure of space-time itself, in the mathematical requirements of relativistic quantum theory, and possibly in the very fabric of space at scales smaller than anything ever directly measured. At every scale and in every context, the same principle. Rotation is the default. Angular momentum is a fossil that never decays. The universe keeps perfect books on this quantity, with an exactness no other system can match. And yet the first entry in those books, the initial condition, the opening deposit, the reason any angular momentum was present to be preserved in the first place, remains invisible. The laws describe what happens to spin. They do not describe where spin came from. They can tell you that everything spinning right now was spinning yesterday, and will still be spinning tomorrow, and has been spinning since the beginning. They cannot tell you why there was a beginning with spin in it. There is a quiet beauty in that gap. It is not a failure of physics. It is a boundary. The laws of physics are descriptions of how systems evolve from whatever initial conditions they are given. Initial conditions are the thing the laws take as input. Asking physics to explain its own initial conditions is a bit like asking a map to explain why the territory exists. The map is extraordinarily good at describing the territory. The question of why there is a territory at all is a different kind of question, and it may require a different kind of answer. Or it may be a question that does not have the kind of answer we are used to expecting. Every time the Earth carries you silently through a night that feels completely still, at over 1,000 kilometers per hour in a direction you cannot feel, you are riding a rotation that was there before the Earth was. The planet formed around the spin. The solar system inherited the spin from a cloud that no longer exists. The cloud inherited it from the turbulent dynamics of the galaxy. The galaxy acquired it through gravitational torques that stretch back to quantum noise in the first moments of the universe. And at the bottom of it all, in the quantum states of every particle making up every atom of your body, there is a layer of intrinsic spin that does not turn because something set it turning. It simply is, built into the definition of matter by the mathematical requirements of physics in a relativistic quantum universe. Everything spins. The whole, adding up, is still. The books are balanced, and the accountant who made the first deposit has never shown their face. If this kind of deep dive into the machinery of the universe is something you want more of, subscribe so you do not miss what comes next. Leave a comment. I genuinely read them. And if there is a topic you want to see explored with this level of depth and detail, tell me below. There are a lot more questions where this one came from, and the answers are worth chasing. End of script, Part 14. The Stern-Gerlach experiment and what quantum spin actually means. We mentioned the Stern-Gerlach experiment briefly when discussing the discovery of electron spin. But it deserves its own extended treatment, because the full strangeness of what that experiment reveals about quantum spin goes much deeper than the surface story of two beams instead of one. The experiment is not just a demonstration that spin exists. It is a window into one of the most counterintuitive features of quantum reality. The fact that before you measure a particle's spin orientation, the particle does not have a definite spin orientation to speak of. Let us reconstruct what happens in the Stern-Gerlach setup very carefully, because the details matter. You send a beam of silver atoms through a region where the magnetic field varies strongly in, say, the vertical direction. Each silver atom has a net magnetic moment because of its outermost electron's spin. An atom whose spin is aligned with the field gradient gets pushed upward. An atom whose spin is anti-aligned gets pushed downward. These are the two outcomes you see. Two spots on the detector, not a continuous smear. Now here is the first subtle point. Before the silver atom enters the magnetic field region, what is its spin orientation? The natural assumption would be that each atom has a definite spin direction, that some are pointing up, some down, some sideways, distributed randomly. The magnetic field simply sorts them according to whatever spin direction they already had. But this is not what quantum mechanics says, and experiments confirm that quantum mechanics is right. Before measurement, the electron's spin does not have a definite direction. It is in a superposition, a quantum state that is simultaneously both spin up and spin down, with certain mathematical coefficients describing the probability of each outcome when a measurement is made. The measurement does not reveal a pre-existing definite spin. The measurement creates the definite spin. Before the measurement, there was no fact of the matter about whether the spin was up or down. This sounds philosophically disturbing, and it is. It means the Stern-Gerlach experiment is not like a filter that separates pre-existing red balls from pre-existing blue balls. It is more like a situation where the balls have no color before they pass through the filter, and the act of filtering causes a color to be assigned. The second subtle and genuinely strange point involves what happens if you run an atom through multiple Stern-Gerlach devices in sequence. Suppose you take the stream of spin-up atoms that exit the first device and send them through a second Stern-Gerlach device, oriented in the same direction, vertically. Every single atom goes through the spin-up channel. That makes sense. The atoms were measured as spin-up, and remeasuring in the same direction gives spin-up again. Measurement is repeatable. Now suppose you take those spin-up atoms and send them through a second device oriented horizontally instead of vertically. Each atom now has a 50% chance of exiting the spin-left channel and a 50% chance of exiting the spin-right channel. The vertical measurement told you the vertical spin, but a horizontal measurement on the same atoms gives random results. Knowing the spin in one direction gives you no information about the spin in a perpendicular direction. The spin components in perpendicular directions cannot both be simultaneously well-defined. This is a quantum uncertainty relationship analogous to the famous position-momentum uncertainty principle. But now the experiment takes a turn that really should disturb any classical intuition still clinging to the picture. Take the spin-left atoms exiting the horizontal device. You measured them as spin-left. Now send them through a third device oriented vertically again. One would expect them all to go up because they were originally prepared as spin-up atoms. But no, half go up and half go down. The horizontal measurement has completely randomized the vertical spin that was established by the first device. The previous measurement result has been erased. What this means is that spin is not something the particle had before you looked. Each measurement creates a definite outcome at the expense of destroying the definiteness of perpendicular components. The particle does not have a pre-existing spin pointing in a specific direction that you are merely discovering. The measurement participates in creating the physical fact. This is quantum mechanics. This is what it actually says about spin. And spin, recall, is a form of angular momentum. Angular momentum, the thing that is conserved across the entire history of the universe, the thing that holds galaxies together and keeps pulsars spinning, the thing encoded in the structure of space-time itself, in theories like loop quantum gravity. This thing, at the quantum level, does not have a definite direction until it is measured. The universe keeps perfect books on angular momentum, but the individual entries in those books do not have definite values until they are read. There is one further layer of strangeness worth mentioning. What spin 1/2 actually means geometrically. A spin 1/2 particle has the peculiar property that if you rotate it by 360 degrees, one full rotation, its quantum state does not return to its starting value. You have to rotate it by 720 degrees, 2 full rotations, to return to the original state. This is completely unlike any macroscopic rotating object. A ball, a spinning top, a galaxy, rotate any of them by 360 degrees, and you get back exactly where you started. But a spin 1/2 quantum state picks up a sign change under a 360-degree rotation. 2 rotations, not one, returns it to its initial state. This is not a quirk of the mathematics. It is a measurable physical property, confirmed in experiments with neutrons sent through magnetic fields that effectively rotate them by controlled amounts. Neutron interferometry has directly demonstrated the 720-degree periodicity of spin 1/2 states. The mathematics of this behavior belongs to the theory of what are called spinors, and spinors require a different geometry than ordinary vectors to describe. The difference is not metaphorical. It reflects a genuine distinction in the mathematical structure of half-integer spin objects in a three-dimensional space, governed by the symmetries of special relativity. Half-integer spin particles live in a mathematical world that is, in a precise sense, topologically different from the world of ordinary vectors and tensors. The space of spin states for a fermion is a structure that covers the space of classical rotations twice. Every classical rotation corresponds to two distinct quantum states. This double covering is not a complication or an approximation. It is exact, fundamental, and confirmed by experiment. It is the mathematical signature of being a fermion rather than a boson, and it is why fermions and bosons behave so radically differently in collective settings. Part 15. Black holes, accretion disks, and the most energetic spinning structures. The most luminous, sustained sources of energy in the observable universe are not stars. They are quasars, quasi-stellar objects, the blazing cores of distant galaxies powered by supermassive black holes actively consuming surrounding matter. At their peak, the brightest quasars outshine their entire host galaxies by factors of hundreds or thousands. They are visible across the observable universe, their light reaching us from epochs when the cosmos was less than 1 billion years old. And the engine driving every one of them is spin. Specifically, the interaction between angular momentum and gravity in an accretion disk around a supermassive black hole. Here is how it works. A supermassive black hole sits at the center of a galaxy, with a mass ranging from millions to tens of billions of times the mass of the Sun. Matter, gas, dust, the disrupted remnants of stars torn apart by tidal forces, falls toward the black hole. But almost none of this infalling matter has zero angular momentum relative to the black hole. It is always coming from some direction, always has some sideways velocity component, always carries some spin relative to the central object. So it cannot fall straight in, it spirals. It forms a disk. The accretion disk around an actively feeding supermassive black hole is one of the most extreme physical environments in the universe. The inner regions of the disk orbit close to the event horizon, moving at significant fractions of the speed of light. Friction and magnetic turbulence within the disk convert the orbital energy of the gas into heat, and the temperature of the inner disk can reach millions of degrees. At these temperatures, the disk radiates across the entire electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. The luminosity is prodigious. The efficiency of this process, the fraction of the infalling mass that gets converted to radiated energy rather than swallowed into the black hole, can be extraordinarily high. For a rapidly spinning black hole, the innermost stable circular orbit, the closest orbit at which matter can stably circle before spiraling in, is much closer to the event horizon than for a non-spinning black hole. And the closer the innermost stable orbit is to the event horizon, the more energy is liberated before the matter crosses the point of no return. For a maximally spinning black hole, the theoretical efficiency of accretion can reach about 42% of the rest mass energy of the infalling material. Compare this to nuclear fusion, which converts less than 1% of rest mass energy into radiation. Accretion onto a rapidly spinning black hole is roughly 50 times more efficient than the nuclear processes powering stars. The spin of the black hole matters directly for how much energy the accretion disk can extract. A rapidly spinning black hole creates a quasar that can shine 1,000 times brighter than a slowly spinning black hole of the same mass with the same amount of infalling matter, because the efficiency of the energy extraction depends on how close the innermost stable orbit can get to the event horizon, and that depends on the black hole's spin. The jets that many active galactic nuclei produce, the narrowly collimated beams of plasma that can extend for hundreds of thousands of light years, far beyond the host galaxy itself, are also powered in significant part by the spin of the black hole. The Blanford's-Najac mechanism, proposed in 1977, describes how magnetic fields threading the ergosphere of a spinning black hole can extract rotational energy from the black hole itself, not from the infalling gas, but from the spin of the black hole, and channel it into the relativistic jet. In this mechanism, the spin of the black hole is the fuel. The black hole loses spin slowly over time as energy is extracted by the magnetic field and launched into the jet. The supermassive black hole at the center of M87, the galaxy whose black hole was directly imaged in 2019 by the Event Horizon Telescope collaboration, is estimated to have a mass of approximately 6.5 billion solar masses and to be spinning at roughly 90% of the theoretical maximum. The jet it produces extends some 5,000 light-years from the galactic center, visible in radio wavelengths. The energy powering that jet, the energy that has been propagating outward for millions of years, lighting up structures larger than many ordinary galaxies, is coming from the angular momentum of a single object roughly the size of our solar system. This is angular momentum at its most spectacular. The same conservation law that keeps a spinning ice skater rotating, expressed in an object 6.5 billion times the mass of the Sun, powering a jet that dwarfs the galaxy it sits in, visible from 55 million light-years away. And consider what this means for the long-term future of the universe. Black holes, once formed, are extraordinarily stable. They evaporate through Hawking radiation. But for stellar mass black holes, this process takes longer than the current age of the universe, by many orders of magnitude. Supermassive black holes will persist for incomprehensibly long times, long after the last star has burned out, in roughly 100 trillion years, long after the last white dwarf has cooled to darkness, in something like 10 to the power of 37 years, the universe will still contain black holes. Spinning black holes, preserving, in their angular momentum, a record of the rotational history of all the matter that fell into them across billions of years of cosmic history. In the very long future of a dark, cold, nearly empty universe, the primary rotating objects will be black holes, and the angular momentum they carry will be the final, patient, extraordinarily long-lived echo of the rotation that began in the molecular clouds that formed the first stars, that eventually formed the galaxies, that eventually produced and fed those black holes. The rotation does not stop, it simply waits. Part 16. The Milky Way's rotation and our place in the spinning disk. We have talked about galactic rotation in the abstract, but let us make it concrete and personal, because we actually live inside one of these rotating disks, and the numbers are staggering in a way that does not always land in the abstract. The Milky Way is a barred spiral galaxy. Its disk is roughly 100,000 light-years in diameter, and somewhere between 1,000 and 2,000 light-years thick in most places, thickening to perhaps 12,000 light-years in the central bulge. It contains somewhere between 100 billion and 400 billion stars, though the uncertainty in that number is itself astronomical. The galaxy is difficult to census from inside. Our solar system sits about 26,000 light-years from the galactic center, which places us roughly halfway out in the disk. We are not in the center, not at the edge, but at a comfortable middle distance in a relatively calm region between two spiral arms called the Orion arm or local arm, a smaller spur branching off the larger Sagittarius arm. The Sun, and everything in the solar system with it, orbits the galactic center at approximately 230 kilometers per second. That is 828,000 kilometers per hour. To complete one full orbit of the galaxy, one galactic year, takes roughly 225 to 250 million years. The Earth is about 4.6 billion years old. The Milky Way has been turning for essentially all of that time. In those 4.6 billion years, the solar system has completed approximately 18 to 20 full orbits of the galaxy, 20 galactic years old. When you say the Earth is old in human terms, you mean something. When you say the Earth is 20 galactic years old, you are saying something different. In the vast time scale of the galaxy's rotation, the Earth has lapped the center only about 20 times. When the Cambrian explosion happened, when complex animal life first appeared in the oceans roughly 541 million years ago, in a burst of evolutionary diversity that transformed the living world, the solar system was on the opposite side of the galaxy from where it is now. The solar system has completed a little more than 2 full galactic orbits since the first complex animals swam in Earth's oceans. Recorded human history, all 5,000 years of it, represents less than a millionth of one galactic orbit. The entire span of human civilization is a blink in the rotation of the galaxy. This is what it means to live on a rotating disk that is large enough that even at 230 kilometers per second, one trip around takes longer than the entire history of complex animal life. The rotation of the galaxy is not uniform in the way a solid disk rotates. Unlike a spinning wheel, where every point on the surface completes a rotation in the same time, the galaxy exhibits differential rotation. The inner regions complete their orbits faster than the outer regions. Stars closer to the galactic center orbit more quickly. Stars farther out orbit more slowly. This differential rotation has several interesting consequences. One is that the spiral arms are not actually fixed structural features that rotate with the stars. If the spiral arms were made of fixed collections of stars, differential rotation would wind them up over time into tighter and tighter spirals, until they smeared out into indistinction. The galaxy is old enough that this would have happened many times over. Instead, astronomers believe spiral arms are density waves, regions of slightly enhanced density that propagate through the disk, compressing gas and triggering bursts of star formation as they pass, then moving on. Stars enter a spiral arm, slow down slightly, then exit the other side. The arm is a traffic jam, not a fixed structure, and new stars continually light up within it, while old ones pass through and out. The bar at the center of the Milky Way, the elongated concentration of stars that gives it the designation barred spiral, is another interesting rotational feature. The bar rotates as a more or less rigid structure, somewhat like a spinning baton, while the surrounding disk shows differential rotation. The point where the bar's rotation rate matches the local orbital speed of disk stars, called the corotation radius, has special physical significance. Near this radius, the interaction between the bar's gravitational influence and orbiting disk material is particularly strong, potentially driving material radially inward or outward and influencing the distribution of gas that feeds star formation. The center of the Milky Way itself, the dense region hidden behind enormous clouds of gas and dust at the heart of the galaxy, harbors a supermassive black hole with a mass of about 4 million solar masses. It is called Sagittarius A, pronounced Sagittarius A star, and it was the second black hole to be directly imaged by the Event Horizon Telescope, with the image released in May 2022. Sagittarius A appears to be spinning, though measuring the precise spin parameter of a galactic center black hole is technically challenging. It is currently relatively quiescent, not actively consuming large amounts of material, but in the past, it has almost certainly had periods of high activity, and there is evidence of large-scale structures, called Fermi bubbles, extending thousands of light-years above and below the galactic plane, that may be the remnants of past episodes of intense energy output from the central region. So when we look at the Milky Way as a whole, the disk, the bar, the spiral arms, the central bulge with its supermassive black hole, we are looking at a structure that has been rotating for billions of years, maintaining its organization through the conservation of angular momentum, continuously forming new stars in its spiral arms, and recycling stellar material back into the disk through supernovae, driven in its rotation by the gravitational pull of both its visible matter and its vast dark matter halo. The Milky Way is not a static backdrop, it is a machine, a spinning, self-sustaining structure that converts diffuse gas into organized stellar populations and back again, powered by gravity and angular momentum, maintaining its shape and rotation across timescales that dwarf any human frame of reference. And somewhere in one of its less distinguished spiral arm regions, orbiting at 230 kilometers per second in a medium-sized planetary system around an ordinary middle-aged star, there are organisms asking why it spins. Part 17. The Coriolis Effect. When planetary spin becomes visible. We introduced the Coriolis effect early in this video as the place where the Earth's rotation makes itself visible in weather systems. Let us go back to it and examine it more carefully, because it is a remarkably elegant example of how the rotation of a reference frame becomes physically measurable and has real consequences for the dynamics of everything moving within that frame. The Coriolis effect was formally described mathematically by the French engineer and mathematician Gaspard Gustave de Coriolis in 1835, though sailors and gunners had noticed its practical consequences for centuries before Coriolis quantified it. The effect arises whenever an object moves in a straight line within a rotating reference frame. From the perspective of an observer outside the rotating frame, the object is moving in a straight line. But from the perspective of an observer within the rotating frame, like someone standing on the Earth's surface, the object appears to curve. The physics is this: the Earth rotates eastward beneath anything moving above its surface. An object moving northward from the equator is also carrying with it the eastward rotational velocity that the equatorial surface has, about 1,674 kilometers per hour. As it moves toward higher latitudes, the surface beneath it is rotating more slowly, because it is closer to the rotation axis. So the object's eastward velocity exceeds the eastward velocity of the surface beneath it, and from the surface observer's perspective, the object drifts eastward, to the right in the northern hemisphere. This deflection to the right in the northern hemisphere, and to the left in the southern hemisphere, is not just a meteorological curiosity. It shapes the large-scale circulation of the entire atmosphere. Without it, the global wind patterns would be completely different. The trade winds, the westerlies, the polar easterlies, the great belts of persistent wind that have guided ocean navigation for millennia, exist in their form because of the Coriolis effect. The ocean circulation patterns that distribute heat around the planet, moderating climates and making large stretches of currently habitable land habitable, these also bear the Coriolis signature. For hurricanes specifically, the Coriolis effect is what provides the initial rotation. A storm begins when a large mass of warm, moist air converges toward a region of low pressure. In the absence of Coriolis, this air would flow straight in toward the low, filling it evenly. But the Coriolis effect deflects the inflowing air, causing it to circulate around the low-pressure center rather than filling it directly. In the northern hemisphere, this produces counterclockwise circulation. In the southern hemisphere, clockwise. The storm grows as more air continues to spiral in, transferring its latent heat to the system as water vapor condenses into clouds. There is a persistent misconception about the Coriolis effect that is worth addressing directly. You may have heard that water drains in different directions down a drain in the northern versus southern hemisphere, counterclockwise in the north, clockwise in the south. This is mostly myth for household sinks and bathtubs. At the scale of a residential drain, the Coriolis force is vastly smaller than the random turbulence introduced by the shape of the basin, the direction the water was filling, and minor imperfections in the plumbing. Household drains can spin in either direction in either hemisphere. The Coriolis effect only becomes systematically dominant at scales of many kilometers. The scale of weather systems, where the fluid has enough room and time to feel the accumulated deflection. At the scale of hurricanes, the Coriolis effect is not just a minor correction. It is the organizing principle. Hurricanes cannot form within a few degrees of the equator precisely because the Coriolis effect is too weak there. The Coriolis force goes to zero at the equator itself, where the rotation axis is parallel to the direction of motion. A storm forming at the equator has no mechanism to acquire the initial spin that would let it organize into a rotating system. This is why the tropical cyclone season always involves storms that form at latitudes of at least 5 to 10 degrees from the equator. Every time you watch a satellite image of a hurricane, that beautiful spiral structure, those sweeping bands of cloud curving around a clear eye, you are watching the Earth's rotation made visible. The hurricane is a direct signature of the angular momentum of a rotating planet, expressed in atmospheric fluid dynamics at the scale of thousands of kilometers. It is the Earth's spin, writing its name in clouds and wind. The Coriolis effect also has practical consequences for long-range artillery and ballistic missiles. A shell fired from a cannon at a target several kilometers away will, if the Coriolis effect is not accounted for in the firing solution, land to the right of the target in the northern hemisphere and to the left in the southern hemisphere by an amount that increases with range. Military artillerists have been correcting for this since the late 19th century. Intercontinental ballistic missiles must apply Coriolis corrections continuously throughout their flight. The rotation of the Earth is not a background fact irrelevant to practical navigation. It is an active physical influence that must be accounted for in any precision targeting system. In a very real sense, every GPS satellite correction, every ballistic trajectory calculation, every long-range weather forecast, every ocean circulation model, every hurricane track prediction is accounting for the rotation of the Earth. The planet's spin is not just a fact about the sky. It is an operational constraint on everything that moves over large distances or timescales on or near the surface. The invisible rotation of the ground beneath you has visible, measurable, practically significant consequences at every scale above the domestic. Part 18. The Spinning Universe and the Open Horizon. There is a perspective that becomes available only after you have followed rotation all the way from the quantum spin of an electron, through the orbital mechanics of the solar system, through the flat rotation curves of dark matter halos, through Gödel's closed time-like curves, to the spin networks of loop quantum gravity. It is a perspective that the beginning of this journey does not suggest at all, but that by the end feels almost inevitable. The question we started with was, why does everything spin? And the most honest answer, gathered from everything physics currently understands, is layered. There is a part of the answer that is complete and beautiful, and represents one of the great achievements of human intellectual history. And there is a part of the answer that points past the edge of what current physics can address, into territory that will require new frameworks, new mathematics, and possibly new ways of thinking about what a physical explanation can even mean. The complete part is this. Once angular momentum exists in a system, the system's rotational behavior is governed by conservation of angular momentum, which follows from Noether's theorem, which follows from the rotational symmetry of the laws of physics. The rotational symmetry is exact, the conservation law is exact, and the result is that every spinning thing you can observe today has been spinning without interruption since before it existed in its current form. The planet spun before it was a planet. The galaxy spun before it was a galaxy. The angular momentum was there first. The structures formed around it. This is understood. The mechanisms are known. The predictions match the observations. This part of the answer is a triumph. The incomplete part is this. Where did the initial angular momentum come from? What set the opening conditions of a universe in which angular momentum was present and distributed in such a way that every subsequent gravitational collapse would produce rotating structures, and in which the net total angular momentum adds to something so close to zero that causality is preserved, but not so perfectly zero that individual structures acquired no spin at all? This part has no answer within current physics. It requires either a theory of quantum cosmology capable of deriving initial conditions from something more fundamental, or a new conception of what initial conditions even mean, or possibly something that current physics does not yet have a framework for at all. The universe is filled with rotation at every scale. It carries angular momentum with perfect faithfulness across billions of years. It organizes matter into spinning disks and orbiting systems wherever gravity finds angular momentum to work with. It builds the structure of matter itself out of particles whose quantum spin is a fundamental, inalienable property of their existence, and whose spin statistics determine whether matter can hold shape or dissolves into featureless plasma. And at the bottom of all of it, deeper than the particles, deeper than the fields, possibly as fundamental as the geometry of space itself, there is the spin, that may not be something that lives inside the universe, but something the universe is assembled from. Every galaxy in the sky is a wheel that has been turning since before the Earth existed. Every star is a gyroscope faithfully preserving angular momentum inherited from the gas cloud that gave it birth. Every atom in your body is broadcasting the quantum signature of intrinsic spin at a frequency so precise It can be used to map the galaxy. Every floor you stand on is solid because the electrons in its atoms refuse, on the grounds of half-integer spin and the exclusion principle, to share the same quantum state. You are not sitting still reading this. You are riding a rotation that goes back to the beginning of everything, on a planet that inherited its spin from a cloud, in a galaxy that inherited its spin from the gravitational interactions of the early universe, in a cosmos that keeps its total rotation books balanced to zero, with a precision that makes the most accurate measuring instruments humans have ever built look crude. The stillness you feel is an illusion produced by physics, working exactly as it should, embedding you so completely in the rotating system that there is no reference point outside it from which to feel the motion. The rotation is not something happening around you. You are inside it. You are made of it. And the reason the floor is solid, and the reason chemistry works, and the reason stars do not collapse, and the reason you can exist at all, to ask this question, is spin. Half-integer spin, and the exclusion principle it produces, and the structures that exclusion principle builds. From the quantum to the cosmic, from the electron to the galaxy, from the Pauli principle to the periodic table to life itself. Everything spins. The books balance to zero, and somewhere in the gap between those two facts, in the space between the perfect conservation and the absent origin story, lies one of the deepest open questions in all of science. Keep watching the sky. The universe is still working on the answer.